So we just saw how to add and subtract polynomials in the previous video or videos, and now we're going to look at multiplying polynomials. Okay, so taking care of another operation. Now remember, with multiplication, there's really two big things to keep in mind. One is the distributive property. Okay, so you guys probably know the distributive property. If you have something multiplying a sum, so if I have a product and a sum combined like this, the factor on the outside distributes and multiplies to each term on the inside. Okay, so we kind of know that general principle of distributive property. We've used it a lot. Also, the other thing to really keep in mind is your exponent rules, particularly the rule where you add powers when multiplying together. So if you have something like x to the m times x to the n, that's going to be the same as x to the m plus n. So we add the powers together when multiplying with the same base. Okay, so those are your two main properties that we're going to keep in mind when multiplying polynomials. And of course, there are times where we won't use some of these, but generally speaking, those are the two main things sort of starting out that we need to keep in mind. You can, of course, one thing I did want to talk about, polynomials come in different sizes. And I didn't explain this in the last section, though it probably fit there when I introduced polynomials, but they do come in different sizes. And the different sizes have names, okay? So a polynomial with one term is called a monomial, okay? So a monomial has one term. A binomial has two terms. And a trinomial has three terms. Okay, so we don't really have any special words to represent anything beyond trinomial, three terms, but at least when you see these three terms, or when I use them, you'll know what I'm talking about. Okay, so monomials have one, binomials have two, and trinomials have three. Okay, so we're going to do a lot with all of these. I think in this section with multiplying, we'll focus on the binomials, but you're going to see monomials and trinomials show up. Okay, and so I'm just going to run through some examples, and just to give you an idea of a variety of different things you might see, and then we'll look at some special cases where there are some things, some special formulas that we can use in certain scenarios, okay? So the first thing, let's look at a couple of monomials multiplied together. If you had something like 3x to the fourth y squared times negative 8xy to the eighth. In this example, again, this is really very similar to what we did in the exponent rule section when we talked about exponent rules. You're just adding the powers when you multiply these together, and then the 3 and the negative 8 just multiply like you normally would. So you have negative 24, and then x to the fourth and x, you add the powers of 4 and 1, get x to the fifth. And then y squared and y to the eighth, again, you add the powers together, you get y to the 10th. And we're really just utilizing this property here where we add the exponents when multiplying by the same base, okay? So this is a new polynomial that would be our final answer. Multiplying the monomials, again, you're not going to need distributive property, because the distributive property requires a binomial or more as one of the factors. Here with two monomials, you're just focusing in on this exponent property. If I were to add a term and make it a monomial times a binomial, I could do that. Something like 5x to the third times 7x squared minus 4x Okay, so there's a monomial and a binomial. Again, you're going to multiply using the distributive property, and when we distribute it to each term, the individual products are going to utilize this exponent rule. Okay, so it's a distributive property and the exponent rule to combine your powers. So in this first, the first multiplication, 5 times 7 is 35. X to the third, x to the second, add the powers, you get x to the fifth. The minus will come down because my sign on the outside is positive. 5 times 4 is 20. X to the third and x, add the powers, you get x to the fourth. Okay, and that's it. All right, so distributive property, again, adding the powers when you have the same base. All right. And of course, if needed at the end of these problems, after you've done the distributing, if there are like terms to combine, you want to combine them. Okay. You probably won't see like terms very often when we're dealing with monomials. And of course, if I had something larger than a binomial here, if I had a trinomial, or if I had 4 or 5 terms, you just distribute the monomial to every term. Okay, not just the first 2, but to everything. That's going to be sort of a key feature here. Okay, I'm going to get rid of some of the stuff. Okay, we can also work with 2 binomials multiplied together. If I had something like x plus 3 times x minus 5, for instance. Okay. Well, of course, you could use the distributive property. Focus on the right side here. This is a difference, and this left side is an object, a mathematical object that can distribute in. Okay. And so I could just take this binomial and distribute into the binomial on the other side. Then I would have x times the binomial and 5 times the binomial, and I'd be able to distribute again as well. This repeated distributive property application results in a sort of a simple summary at the end, in which essentially every term on the left distributes and multiplies to every term on the right. Okay? So essentially what we need to do is make sure that each term on the left multiplies each term on the right. We have an abbreviation for that, and many of you have probably seen this before. It's called the FOIL method. I hesitate to write it up here because it's not going to work for everything, but I'm going to show you just because you're probably familiar with it. You multiply the first two terms together, then you do the outer 2 terms together. Okay, and essentially what that does is it takes the first term from the left binomial and multiplies both terms on the right. Then the I is for the inner 2, the 2 on the inside. That's the 3 times the x, and then the last is the L is for last, which are the last 2. Okay, so you have the last one on the left and the last one on the right multiplied together. Essentially, again, we want every term on the left to multiply every term on the right, and this abbreviation will help to make sure we don't miss anything, right? So first times first, outer times outer, right? Then we have inner times inner, and last times last. Okay, so that's how we would multiply that out. But again, just remember, every term on the left must multiply by every term on the right. Okay, and if you remember that general principle, you don't need the FOIL method. You just got to make sure everything multiplies out. So let's go through and do that. X times x is x squared. X times minus 5 is minus 5x. 3 times x is 3x. 3 times the minus 5 is minus 15. Okay. And then, of course, if there's like terms, couldn't get the word out. If there are like terms, you add those together. So -5 and +3 add up to -2. So we get x squared minus 2x minus 15, okay? And so this is the final polynomial. Okay, now that FOIL method is nice, but again, make sure every term on the left multiplies every term on the right. You're gonna probably get sick of me saying that, but that's gonna be a repeated pattern as we move forward. If I were to expand this and give you some examples with larger polynomials, some trinomials and mixing trinomials, mixing binomials, we could even get 4 or 5 terms in here if we wanted to. That pattern will hold where you multiply every term on the left by every term on the right and then combine like terms at the end. So if I had something like x plus 4 times 3x cubed minus 8x squared plus 7x plus 2. Again, I want to multiply every term on the left by every term on the right. So I'm going to start, and the way that I usually organize this is to start with the x, whatever the first term on the left is, and multiply it to every term on the right, and then I go to the next term on the left and multiply it by every term on the right, okay? Obviously the FOIL method won't work here because you could do the first and the outer and the inner and the last, but you're missing a bunch of stuff. You would miss, I don't know, maybe 4 more terms, right? There should be 8 terms total when I'm done with this. So I'd be missing half of them. Okay, so we don't want to use FOIL method when we get things bigger than binomials. All right, so instead I'm going to have the x multiply everything on the right. Let's do that. X times 3x cubed is 3x to the 4th, again adding the powers there. X times -8x squared is -8x to the 3rd. And then x times 7x is 7x squared. X times 2 is 2x. Oop, I missed my square. And then I move over to the 4. And I go 4 times 3x cubed is 12x cubed. 4 times -8x squared is -32x squared. 4 times 7x is 28x. And 4 times 2 is 8, right? Notice again, I mentioned this a moment ago, but there are 8 terms. 1, 2, 3, 4, 5, 6, 7, 8 terms, okay? And that should always be the case. A good check is to, if you multiply the number of terms on the left and the number of terms on the right, 2 times 4, you get 8. And you should always have 8 terms then in that next line. Then you can go through and combine like terms. Well, there's only one term with a power of 4, so that's going to stay. There are 2 terms with a power of 3, so I combine those. -8 and 12 make a 4. There's 2x squared terms, so that's going to make, what's that, -25? Yeah, -25. Mental math is slowing down here. -25. And then there's 2x terms, that's going to be a 30x. Better get that one quick. And then there's only one constant, the 8 hanging out on the end, okay? So in the end, we end up with 1, 2, 3, 4, 5 terms, but that's only because we were able to combine some of the original 8 together. Okay. All right, and that's it for that problem. So that one is fully simplified, okay? Okay, so now we've kind of looked at some of these smaller examples and worked our way up to bigger ones. Maybe we'll do one more where we get a couple of bigger ones together. Maybe we'll do 2 trinomials this time. So let's do let's do x squared plus 3x minus 5. And let's do 2x squared minus x plus 3. Alright, so again, every term on the left must multiply every term on the right. I sound like a broken record, but that's what we want. So I start with the x squared. I'm going to multiply it by everything on the right. So x squared times 2x squared is 2x to the fourth. Again, adding powers. Then 2x squared times negative x is negative, I said that wrong. X squared times negative x is negative x cubed. And then x squared times 3 is 3x squared. Okay, so that gives me my first three terms. Then I want to jump over to the 3x. I get 3x times 2x squared is 6x cubed. 3x times negative x is negative 3x squared. 3x times 3 is 9x. Okay, so that takes care of the 3x. Now I jump over to the minus 5. Minus 5 times 2x squared is minus 10x squared. Negative 5 and negative x is positive 5x. Negative 5 times 3 is negative 15. Okay. Now notice, if I take the original 3 terms times the original 3 terms, I get 9 terms. Should get 9 terms. Let's count them. 1, 2, 3, 4, 5, 6, 7, 8, 9. So I didn't miss anything in theory. Okay. So I've got my 9 terms. And now I have to combine the like terms that are present. So I start out, I've got only a single x to the fourth term, degree 4. I have 2 degree 3 terms. I add them together, I get 5x cubed. I have 3 x squared terms. When I combine them, I get 3 minus 3. Those actually cancel out, add up to 0. I get minus 10x squared. So 4, 3, 2, 3, 2, 2. So I have 2x terms. That makes 14x. And finally, I have that minus 15 down on the end. Okay, that's everything that we need for that to combine those like terms. That takes care of everything. And so now we have a final answer. Okay. In the next video, I'm going to show you some special formulas that we could use when we have special cases of multiplying polynomials. And we'll kind of go back to some of those binomials we saw earlier. We won't probably get into special formulas for larger things just yet.